Hey, welcome back. This is Calc 2, continuing on Chapter 8. We're going to need to work with limits in the last section of Chapter 8. So you're going to see these weird integrals that have kind of infinity symbols on them. So we're going to need to be able to figure out a way to deal with that. And it has to do with limits. Okay, so all the old limit rule stuff kind of we need to have encoded in our brains somewhere. So I'm going to try to kind of do a little review of some limits and see how that goes. Okay, so there's kind of the standard just fill in the blank type limits. So for instance, the limit as x goes to 5 of, x minus 1 all over x squared plus 2, right? Or x squared plus 1, whatever. So the way to figure these out, and it's equivalent to a condition of continuity, right? So if you just plug the number in and you get some output, basically the function is continuous there, and the limit is equal to f of x, or in this case like f of 5. So to figure out this limit, you just plug in 5, so you get 5 minus 1 all over 25 plus 1, which is 4 all over 26, which is apparently 2 over 13, right? Okay, those were always the simplest limits, and then we kind of stumbled upon these things that have discontinuities in them, right? So things like this, x minus, x squared, let's say x squared minus 16 all over x minus 4, right? You may recall we call this indeterminate form. If you plug 4 in here, you're not going to get a nice output. It's not continuous at 4. If you plug in 4, you're going to get 0 in the top, 16 minus 16. You're going to get 0 on the bottom. So the way we kind of dealt with these issues was to simplify. So you could write an equivalent expression for all that the original function, the x squared, the rational function thing, would be equivalent to this expression at all numbers except at and this limit should be going towards 4. Sorry. The new expression will be equivalent to the old expression at every point except at 4, but that's okay because limits don't really care about anything except the approach to the x equals 4. We don't care what happens exactly at there. That's a continuity issue, right? So anyways, if you remove those, you can take the limit as x goes to 4 of x plus 4, and then it's just plug in the 4 and you get 8. Okay, so those were two types of discontinuities, or sorry, two types of limits we looked at. The second one is indeterminate, and today we're going to talk more about these type of forms. And it turns out like there's like 4 or 5 different versions of this, and we're going to have indeterminate. We're going to have some new tools, basically L'Hopital's rule, which will allow us to work with these indeterminate forms. Okay, so we'll work with L'Hopital's form here in a bit. Let's look at some other forms. So that would just be kind of okay. So an infinite kind of forms. So if you had the limit as x goes to infinity of something like, we'll say, I don't know, 3e to the x, right? This thing, where does it end up going? You could always kind of think in terms of a table. You have your x, and then you have 3e to the x. So as x goes to infinity, so, you're thinking like 10, 100, 1,000. Where does 3e to the x go? And if you already know all this stuff about limits, you can just fast forward this part of the video. But okay. So where does it look like it's going? Well, as you plug in bigger and bigger numbers, you'll have either 10, either 100, either 1,000. That's a huge number, right? So for any number you provide me, I can find an x value such that when I put it into this expression, the output will be bigger than the number you imagined. And that's kind of their definition of an infinite limit, right? So we had things like that. You could go towards like like if you have the natural log function and we go towards 0 from the right, so if you had limit of ln of x as x goes to 0 from the positive numbers, that the y values, as you get closer and closer to 0, the y values go lower and lower and lower. And again, it's one of those games. For any negative number you give me, I can find a negative number that is basically below that number you give me in this orientation, and therefore, okay, so it goes to negative infinity. And but then there were ones like this. Limit as x goes to, say, infinity of 5 all over x, we'll say x cubed, right? This form, if you took my class last time, I call it L all over infinity. And whenever you have those cases, it's always going to be 0. And we could use these cases in order to kind of figure out what happens when you have these weird polynomials, like these ratios of polynomials, in other words, rational functions, like 5x cubed plus 2x plus 1 all over 7, x to the 5th plus maybe 2x plus 1 again. You can multiply top and bottom by 1 over x to the 5th times 1 over x to the 5th, and you end up with the limit as x goes to infinity of 5 x cubed over x to the 5th would be 5 over x squared plus 2 all over x to the 4th plus 1 all over x to the 5th all over 7 plus 2 all over x to the 4th plus 1 all over x to the 5th. And then these little parts are all L over zeros, right? So this will go to 0, this will go to 0, this will go to 0, this goes to 0, this goes to 0, and you're left with 0 over 7, which is just 0. Okay. My shortcut for working with these big, ugly, rational guys is to kind of go 5x cubed plus, I can rewrite it. But my shortcut, rather than to use this kind of multiply or divide by the highest degree term and all of the terms, the shortcut is to just kind of pick off the high degree parts from the numerator and denominator and take the limit of that, and you get the same answer. So look, it's 5 all over 7x squared, and of course that's just an L over infinity form, which will go to 0. Okay, and there are 3 variations on that theme, right? So there's the there's the one where the numerator and denominator have the same degree. So maybe like 2x cubed minus x plus 1 all over 5x cubed minus 2x squared plus x, right? To figure out that limit, again, you could divide everything by x cubed, but it's easier just to kind of pick off the high degree terms here and then work with that. So you'd end up with 2x cubed all over 5x cubed. In other words, the limit of a constant, 2/5, which is just 2/5. Right? The limit of a constant is always just the constant. The last variation on that theme was to have a numerator such that its degree exceeded the denominator degree. So maybe something like 5x to the 5th minus x squared plus 2 all over 3x cubed. Let's make it interesting. So negative 3x cubed plus 2x minus 1. Okay. So again, all you need to do is pick off the high degree terms and consider that limit. Okay, so you'd have 5x squared all over 3, and in this case it's negative. I lost my negative symbol somehow. And then you just, that as it goes to infinity, this is an upside down parabola, so it's going to go to negative infinity if you think about the picture. Right. So with regards to polynomials, that's what this thing is. It's some sort of upside down parabola. So as you go towards infinity, the y values are going to go really, really down towards negative infinity. Okay. So those are the 3 main forms. That, in general with polynomials, there's going to be 4 types of behaviors. if your leading coefficient is positive, so if a is positive and the degree of your polynomial is even, your picture is going to be something like this, right? So as you go to negative infinity, it's positive infinity. As you go to the positive infinity, the output is positive. So say something like the limit as x goes to infinity of positive 5x to the 10th power plus 11x cubed minus 12. Based on that picture, as I go to positive infinity in this direction, the function's going up and up and up and up. So it'll be positive infinity. Just like the limit as I go to negative infinity of the same thing will also be positive infinity. Okay, then if you have sort of the other case, which is what we just saw with this negative 5x squared over 3, the leading coefficient is negative and the degree is even. In those cases, you're going to negative infinity in each case. So maybe a simpler version of a polynomial in these cases, something like negative 3x to the fourth plus 2, right? That's going to go to negative infinity because of the picture. Whoops. So maybe I have I got so many of my office hours. Hold on. Okay, so right. If you're going in the other direction to negative infinity, then you have the same issue, right? It's just going to go to negative infinity based off the picture. So you're thinking about where do the y values go as the x values go to negative infinity. Then for the odd functions like the cubics and stuff like that, if a is positive and the degree is odd, you're coming in from the bottom and then it's doing some business and then it's shooting out like that. So as it goes towards negative infinity, it's going towards negative infinity. As x goes toward positive infinity, it's going to positive infinity. So if you had something like the limit as x goes to infinity, let's make sure I'm recording. Yeah. Okay. Limit as x goes to infinity of something like 3x to the fifth minus x plus 1. That's just going to be positive infinity, right? It's based on this part of the picture, this blue part. If you have then going to negative infinity, then you're kind of looking at this other part. It's going to go to negative infinity, right? So the limit as x goes to negative infinity of 3x to the fifth minus x plus 1 will be negative infinity. And then you could play the same game sort of over here. If you have a negative leading coefficient, it's just going to flip the behavior. Okay, so then it will come out towards the bottom, and this is the case when the leading coefficient is negative, but the degree is odd. Okay, so you'll end up with stuff like the limit of negative 3x cubed minus 1, and of course that'll be positive infinity as x goes, whoops, it's negative infinity as x goes to infinity, and then it's reversed, right? So then the limit as x goes to negative infinity of this thing, negative 3x cubed minus 1 is it's positive infinity in that direction based off the little arrows. Okay, so you know, rational functions back up here are basically just ratios. So if you do end up with the higher degree term in the numerator, so for example, x goes to negative infinity of 3x to the fifth minus x plus 1 all over negative 3x cubed minus 1. You could take the ratio, right? So you end up with the limit as x goes to negative infinity of negative, that'll become negative just x squared, right? And then where does that go as x goes to negative infinity? Well, it's even degree, negative front, and then as we go towards negative infinity, it's going down towards negative infinity. So the answer there would be negative infinity. Okay. yeah, so there's a crash course in evaluating rational functions. These rational functions that we looked at, these 3 different versions, we're going to look at again in this section. Yeah, we'll look at these again. These are all indeterminates because if you put in infinity in the numerator on this guy, leading coefficient positive, odd degree, so it's going to infinity. Same for this. It's infinity over infinity. And that's similar to this 0 over 0 stuff that we had back in Calc 1. Okay, 0 over 0. This one is infinity over, what's this guy? This one guy is infinity over infinity as well. This guy here is infinity over negative infinity. So any of those types are called indeterminate. And you can do this kind of analysis with the polynomials and stuff. And you're just looking at the first couple terms, but you can also do what's called L'Hopital's rule, which we're going to show you how to do here in a bit. But anyways, let's keep on going with the kind of these forms and classifying these. So we had L over infinity. We can also look at something like L over 0 forms. So let's say the limit of 1 all over x minus 1 as x goes to 1 from the right. Okay, so this form is L, and if you put in 1, you get 0. So L, I just mean some number, right? I could have like 3 up here. It doesn't really matter. Okay. To figure these out, it's always either positive or negative infinity. Okay, it's either one or the other. You got a 50-50 guess. To get it right, what I suggest you do is a test value. So pick something close to 1. So here's my x, and then 3 over x minus 1. Pick something like, and I'm coming in from the right. So here's 1, and I'm coming in this direction. So I need to pick something like 1.1. Okay. If I was coming in from the other direction, I'd pick 0.9. So if you plug 1.1 into 3 over x minus 1, you get a positive. The 3 all over 1.1 minus 1 is a positive. Positive divided by a positive is positive infinity. Okay, let's try one more of those. So x goes to 2 from the left of negative 5 all over x minus 2 squared. Okay. Again, it's either positive or negative infinity because the top is just some number and the bottom is 0. So this time I'm coming in 2 from this direction, so I'm thinking numbers like 1.9. If I plug that into my formula, I get negative 5, which is negative, all over something squared, which is positive. Negative over positive is negative, so my answer is negative infinity. So those are L over 0 types. Then you can get all these infinity times infinity times negative infinity. So for example, the limit as x goes to infinity of x e to the x. Okay. Each one goes to infinity on their own. So you have like the limit as x of x as x goes to infinity goes to infinity. Okay, the limit as x goes to infinity of e to the x, that also goes to infinity. And it turns out you can kind of just multiply the infinities together. Depending on the signs will matter. So if it's positive infinity times positive infinity, you end up with positive infinity. Take that and compare it to something like this. We have e to the x times ln of maybe something like 1 over x. So in this case, the first part is going to go to positive infinity. This part, when you plug in big numbers into 1 over x, it's going to go to, so it'll be 1 over infinity, which will be 0 eventually. And it'll be basically like approaching 0 from the right on the natural log. So on the natural log, you're kind of coming in this direction. And that thing will go to negative infinity. Okay. So even if you didn't understand that, the point is that your answer is going to be negative infinity because infinity times negative infinity is negative infinity. You think of it that way. Okay. Other forms that you might have seen, infinity plus infinities. So it's stuff like the limit of x squared plus e to the x as x goes to infinity. This is just infinity because each one is going to infinity. So infinity plus infinity is equal to infinity. Negative infinity minus infinity is equal to negative infinity. But here's kind of the trouble. Infinity minus infinity types are indeterminate. So don't get a false sense of security. You have to do special methods on that form. And that's kind of what we go through in this section here eventually. Something like the limit as x goes to 0 from the right of x over the natural log of x. The numerator is 0, but the denominator is infinity. And the way this kind of will work is kind of like 0 times 0. And if you want to, and it's negative infinity, you could kind of think of it at each point. The numerator is kind of like x times 1 over ln x, right? So as you're plugging in values for x, let's say 0.1, you're going to have something small times something that is getting really big negatives. So I don't know what ln of 0.1 is. Let's use a different number, right? Let's use something that we can figure out the ln of really quick. So something like something close to 0. So e to the negative 10. Okay. So you'll have something e to the negative 10, which is 1 over e to the 10, which is pretty close to 0, times 1 over ln of e to the negative 10, which is negative 10. And then e to the negative 100. Right? So you have e to the negative 100, which is really, really super small, times 1 over negative 100, which is also getting smaller. So it kind of works like a 0 times a 0, and you'll end up with a 0 at the end. The reverse, you could take the reciprocal of that thing, and then it'll end up being infinity. So if you could produce all these kind of like limit rules if you get really into it. So in this case, it's sorry, I didn't flip it. ln x over x. And in this case, you'll have negative infinity over 0. And if you have something like 1 over 0 or L over 0, we know that goes to infinity. Okay, so it's kind of like you have negative infinity times another infinity, which will be some variation of infinity. You just have to worry about the sign. So because we're coming in from the right, the 1 over x will go to positive infinity. So ultimately, your answer will end up being negative infinity. So these are all, they kind of won't teach you how to do things like this one or this one. They kind of assume you can figure those out. If you have real trouble, you just make one of these tables, right? And kind of go by where the numbers seem to be going. You don't always want to be doing the tables, though, because you'll be there forever, and you'll never get through a test, especially if you have something else that's demanding, like a integration, a trigonometric integral or something like that. You're not going to have time to fool around with these. These should be easy problems, right? So anyways, that's what's on the chopping block today. So let's now officially kind of get in to 5.6. This all has been pretty much a review. Let's now dive into 5.6, okay? So now it's kind of like 5.6. So hopefully if you're fast forwarding, this is where we're starting. L'Hopital's rule and some new indeterminate forms, okay? So indeterminate forms / L'Hopital's rule. It's not like hospital. It's not French for hospital. That's the guy's name. And supposedly he stole this process from somebody else. So anyways, first we want to look at these sort of ratio of polynomials and kind of rehearse those, right? So there were 3 types, and what I like to call these are kind of Calc 1 remedies for indeterminate forms. So I kind of want to outline what are those indeterminate forms that we already know. So the first one we already know is a 0 over 0 form, and I alluded to that above. Okay, so I'll just write it out again. We can make up a new one, like x goes to 5. These are easy to make, right? X minus 25. Maybe all over x minus 5. You could factor the numerator limit as x goes to 5, x minus 5 times x plus 5. And then you could remove these. So it's kind of a removable discontinuity type thing. X plus 5, and then you get 5 plus 5 is 10. Okay, great. So that's the first type. The second type, which we're talking about with the polynomial stuff, is the infinity over infinity. And there's basically three different variations on that theme. So let's, again, kind of take a look at three variations of this. Let's make one going to negative infinity. So the first is when the denominator has a degree greater than the numerator. So maybe like x cubed minus 2x squared plus 1 all over x to the fifth minus 3x plus 1. Okay. The denominator's degree is greater than the numerator. So the way you can approach this is just to consider those high degree terms that I've circled and take that limit. And it turns out that works. Okay. So you may have learned it different in Calc 1. I showed you the Calc 1 way above. If you fast forwarded, though, I'm kind of re-explaining it. So this is the L over infinity type, which is always just 0. Okay, so that's the first type. The second type is when the numerator and denominator have the same degree. So again, let's go to negative infinity. 5x cubed minus 2x plus 1 all over 2x minus 3x cubed plus 5. So on like AP tests, they'll kind of try to trick you. You have to pick off the high degree terms. You can't. It's not 5x cubed over 2x. It's that. So limit as x goes to negative infinity, 5x cubed all over negative 3x cubed, which is just going to end up being negative 5/3. Okay, when you reduce, and then the limit of a constant is just a constant. Then the third case is when the denominator's degree exceeds the numerator's degree. So let's go with negative infinity again. So say 2x cubed minus 2x plus 2 all over 5x to the fourth minus 3x plus 1. Okay. So you take the limit as x goes to negative infinity and just pick off the high degree terms again. I'm sorry if I'm going too fast. I feel like I'm smushing all this in, and I just want to make sure. Okay, just breathe. Okay, so what is this if you reduce? It's 2 all over 5x. Okay. Whoops, so I meant to make the degrees. No, I meant to make the degree in the numerator bigger than the denominator, sorry. Okay. That's what happens when I rush. Let's just do that. Fix. And then I could change this to a 5. Okay. And then this will change. I apologize. This will be just 2x. So 2x over 5 as x goes to negative infinity. That's an odd degree. It's basically the equation of a line. So as we go towards negative infinity, the y values are going to negative infinity as well. So this one would be negative infinity. Okay, so that's Calc 1 stuff, Calc 1 remedies. Let's now move into then L'Hopital's rule. Okay, so section 2, L'Hopital's rule. Okay, so this is from theorem in the book. I don't remember which one it is. It's just a theorem. Basically, it says if you're taking the limit of two functions, and it doesn't have to be like a polynomial over polynomial, just in general, two functions, and you sort of investigate it, and it turns out it's 0 over 0, or it's some variation of infinity over infinity, right? If it's any of those forms, then you can go ahead and take the derivative. So this isn't the quotient rule. You're just literally taking the derivative of the numerator and putting it in the numerator, and then literally taking the derivative of the denominator and put it in the denominator. That thing will have the same behavior. So we'll act the same. Or we'll act like the limit of f of x all over g of x. Okay. Assuming that you can actually evaluate this thing. So assuming this exists, or even if it's infinite, that's okay too. Okay. There's a lot of proofs of this, and there's no like simple way to kind of hand it to you. One way they do it is kind of so a simple version, the simplified version with some assumptions to make it easier. Simplified version proof. If you have f of a equaling g of a, which is the number you're approaching with the limit, and you know that f prime and the derivative of g are continuous, and also that g prime of a does not equal 0, then you can note the limit as x goes to a of f of x all over g of x is equivalent to the limit as x goes to a of f of x, and these should all be equal to 0, sorry. So if f of a and g of a are equal to 0, then you could basically add it in or subtract it in the numerator, right? So f of a and then g of x minus g of a, and you've not really done anything, but you set yourself up to kind of produce the limit definition of the derivative. So if you remember f prime of a, you can rewrite that as a limit as x goes to a of f of x minus f of a all over x minus a. And that's kind of what we're after. We want to do a substitution to get L'Hopital's rule. So once you're here, you can multiply top and bottom by x minus a. All right, so you can multiply basically not x minus a, but 1 over x minus a. So you end up with basically the limit of the ratio of the derivatives. But this only works in that one particular case. And it becomes a little more messy, I guess, with if you try to do it in general. So anyways, this top part here then is just f prime of a, and then the bottom part right here is your g prime of a. So hopefully that kind of convinces you, at least in this one case, it seems to work. So we'll go with your word on it, right? So hopefully you can. Okay. So anyways, let's we can kind of revisit these polynomial kind of questions again. So let me borrow this guy, the x squared minus 25 over x minus 5, which we're saying is equal to 10. And let's do L'Hopital's rule on it and see if that works. Okay, so example, revisit limit of x squared minus 25 all over x, was it minus 5, as x goes to 5. Okay, so first notice this is a 0 over 0 form, which is you have to have one of those forms to use L'Hopital's. You can't just use it whenever you feel like it. Okay, so that is one of the forms. So you just take the derivative of the top. The derivative of x squared minus 25 is 2x. The derivative of x minus 5 is 1. Okay, and then it's just substitute, right? Put 5 in for x and get 10. And sure enough, that's what we got above, doing the hard way. One awesome thing is now you no longer have to memorize this formula. So if you took Calc 1 with me, we had to have this thing memorized. It's basically, right now as it sits, it's 0 over 0, right? The memorized version is just 1, but now you could do L'Hopital's on it and get the answer. So now we can do things we couldn't do back in Calc 1 beyond just memorizing it. So anyways, you take the derivative of sine is cosine. Derivative of x is 1. Cosine of 0 is 1. Okay. Great, good stuff. Let's look at some of the ones in the book then. Let's look at some examples here. Limit. Let's look at another trig one. As x goes to 0 of sine of 3x all over sine of 5x. Plugging in 0, you get 0 over 0 form. So we could do L'Hopital's on it. So the derivative of sine of 3x is cosine 3x times 3. The derivative of sine 5x is cosine 5x times 5. And then check the form again. So you could keep on doing L'Hopital's so long as it's in the 0 over 0 or infinity over infinity form. If you plug 0 in here, though, you just get the answer, which is cosine of 0 is just 1, so it'll end up being 3/5. Okay. Let's look at another one. Limit as x goes to 0 of the arc sine of x over x. If you don't remember arc sine is from the restricted version of sine. So we restrict it from negative pi over 2 to pi over 2. And then we could rotate it about the line y equals x. And the picture ends up looking like this. But anyways, as we approach 0, arc sine is equal to 0. And as x approaches 0, x is equal to 0. 0 over 0 form, so we could do L'Hopital's. The derivative of arc sine is 1 all over the square root of 1 minus x squared. Derivative of x is 1. Plug in 0, and you just get 1 over square root 1. So 1. So you got a lot of 0 over 0 forms there. Let's look at one infinity sort of type. Well, let's not. I mean, all those polynomial types are infinity over infinity, right? Let's limit as x goes to infinity of something like e to the x over x cubed, right? So this is infinity over infinity. X cubed is going to infinity. So you could do L'Hopital's. So you get e to the x derivative of e to the x is e to the x all over 3x squared. That thing is infinity over infinity again. So again, take derivatives. That thing is infinity over infinity again. So you just keep on doing L'Hopital's until you get something to work with. So it'll be e to the x over 6, and then you can figure that out. That'll just go off to infinity. Okay, so it's like a fight between the two, numerator and the denominator, and eventually one or the other kind of wins. Okay, let's look at the other indeterminate forms then. So these are pretty simple, pretty easy. The other ones are a little more worth more points, right? They're a little difficult. They always turn into L'Hopital type problems, though. Okay, so the first form is 0 times infinity. So the way you handle these is to first rewrite it as a fraction. In particular, usually a complex fraction, like 1 over x or something like that. And then secondly, you'll apply L'Hopital's. Okay, so let's take a look. Here we have the limit as x goes to infinity of x times sine of 1 over x. Okay, so the form, make sure it's in our form. X is going to infinity. Sine of 1 over x. As x goes to infinity, 1 over x is going to 0, and then sine of 0 is just 0. So we have our infinity times 0 form. So what you do is rewrite x as 1 over x. And then you have this new fraction, sine of 1 over x all over 1 over x. Okay. Okay, so now in the numerator, sine of 1 over x as x goes to infinity is sine of 0, which is just 0. And the denominator, 1 over x as x goes to infinity, that will also, be 0. Okay, so you can do L'Hopital's. So that's what I do. Derivative of sine is cosine. And then the chain rule, I have to tack on the derivative of 1 over x, which is negative 1 over x squared. Downstairs, then the derivative of 1 over x is negative 1 over x squared. And then we got a nice cancellation. And we have the limit as x goes to infinity of cosine of 1 over x. And that'll just then be cosine of 0 because it's one of these guys. You can kind of move the limit inside the cosine function and take the limit of 1 over x. So I want it being cosine of 0, okay, which is 1. Okay, so there's those kind of problems. The next kind are kind of these weird exponentiated versions. So 1 to the infinity, infinity to the 0, 0 to the 0. So the way you do these is to rewrite your function as an exponential. The book does it a little differently than I do, and you could do it the book way if you want, but I think my way is just as good. Exponential. So how do I do that? If you have something like 2 to the x, you can always rewrite that as e to the ln of 2 to the x, and then rewrite that as e to the x ln 2. Secondly, after you do that, then you're going to slide the limit into the exponent. So the idea is just like the idea of the previous problem where I slid the limit inside the function. Okay, you'll do the same thing, but instead of inside, it looks like you have the limit of e to the x, and you're basically rewriting it as e to the limit of x. So that's kind of what I mean. Thirdly, then, you usually end up having to do some L'Hopital's. So use above methods and finish off the problem or evaluate it. Okay, so let's look at one or two of these characters. Example. The limit as x goes to infinity of 1 plus 1 all over x to the x. Okay. So if you look at the form, as x goes to infinity, the inside part here will go to 1, and then the exponent will go to infinity. So it's 1 to the infinity form. Okay. So the first thing I do is rewrite it as e to the ln of 1 plus 1 over x to the x. Okay. Then I'm going to use a power rule to bring this down in front. So I end up with the limit as x goes to infinity of e to the x ln of 1 plus 1 over x. Then I'm going to slide the limit up into the exponent. So I have the limit as x goes to infinity of x times the ln of 1 plus 1 over x. And then I look at the form, right? So if x is going to infinity, this part will go to infinity, and then the ln of 1 will go to 0. Because it's ln of 1 plus 1 over x. 1 over x will go to 0, and then you'll have ln of 1, and ln of 1 will be 0. So it's infinity times 0 form, so you're going to have to rewrite it as a complex fraction. So you have e to the limit as x goes to infinity of the ln of 1 plus 1 over x. I'm going to find a common denominator and rewrite it as x plus 1 over x, and then all over 1 all over x. Okay. The numerator now goes to 0, and the denominator now goes to 0. So you're going to be able to do L'Hopital's. So in the numerator to do L'Hopital's, what's a little bit easier on my brain is to use the log rule to rewrite it as a difference, and then take its derivatives. Okay, so I'll end up with e to the limit as x goes to infinity of 1 all over x plus 1 minus 1 over x all over the derivative of 1 over x, which is negative 1 over x squared. I'm going to clean that thing up and see if it's really paid off, right? So I got 1 over x plus 1. Probably just get a common denominator here, right? So either multiply top and bottom by x minus 1 over x, and I multiply top and bottom there by x plus 1. Right, so it's all of this divided by this negative 1 over x squared. So e to the limit as x goes to infinity of, in this numerator here, when I combine the numerators over the common denominator, I'll have x minus x plus 1, which will be x minus 1, which would just be minus 1. Okay. So in the numerator there, I'm getting minus 1 all over x times x plus 1. Then I'm multiplying, so instead of division, you write it as multiplying by reciprocal. So you multiply by the reciprocal of that thing, so x squared all over 1. Okay. So you get e to the limit as x goes to infinity of negative, and this should have been negative, so negative times negative is positive. That will clear up. And I'm left with x squared all over x squared plus x when if you distribute this. That thing is infinity over infinity. So you can do L'Hopital's again, or you can just remember what I said about taking limits of polynomials. It'll work like the limit of x squared over x squared, which is 1 over 1. So the limit of that rational expression is 1. You just end up with e as your answer. So if you didn't get that, it's the limit. This limit will be basically just x squared over x squared, and then you could simplify that. And the limit of 1 is just 1. So you get e to the 1, which is e. Okay, let's look at one more, and this will be the video quiz question. Video quiz, video quiz, video quiz. So the limit as x goes to 1 from the right of the ln of x raised to the x minus first power. Video quiz, video quiz. So we have this, and then we have one more form, and then that'll do it. All right, so let's take a look. First, I rewrite it as an exponential. So I have e to the ln of ln x to the x minus 1. Okay. Then I use power rule to bring this down in front. E to the x minus 1 ln of ln x. Then I move the limit inside the exponential. Then I check out the form. So x minus 1 as x goes to 1 is just 0. The inner part here, so you kind of bring the limit inside the natural log of the natural log of x. Take the limit of the natural log of x as x goes to 1. Right? So if you remember the graph, as x goes to 1 from the right, eventually your ln of x is going to go to 0. Okay, so you're kind of asking yourself, what is the natural log of 0? And as x goes to 0, ln of x goes to negative infinity. Okay, so what you're going to end up with is 0 times negative infinity, which is one of our indeterminate forms, the first one of the harder ones we looked at. And so you can rewrite it as a complex fraction. So you get ln of x all over 1 all over x minus 1. Okay. And then look at that form again. So this form here is the the numerator is 0, right? Because ln of x is going to whoops, the numerator is in negative infinity. I apologize. We kind of already figured that out. The denominator is of form 1 over 0. And we're coming in from the right, so it's going to be positive infinity. If you wanted to, you could kind of, to the side, do a little work in your margin. Okay, so this thing is L over 0 form. You come into 1 from the right, so test valuing it, you're looking at something like 1.1, so you're going to get a positive number over a positive number, which is positive infinity. Okay, so that thing at the bottom is positive infinity, so you can do L'Hopital's on it, which don't look like a lot of fun, but we can do it. Okay, so you go with 1 over ln of x, and then chain rule times the derivative of ln of x is 1 over x, all over negative 1 all over x minus 1 squared. Okay. So all of those forms, like y equals 1 over something, the derivative y prime will always be, because this is just u to the negative 1, it'll be negative u to the negative 2 times, if you need a chain rule, but it's always going to be just negative 1 over u squared. Okay, so that's how I kind of do those quickly. 1 over x minus 1 is negative 1 over x minus 1 squared. Okay. Okay, so e to the limit as x goes to 1 from the right now of basically 1, I'll rewrite this using the commutative multiplication rule, x ln x, divided by, in other words, multiplied by the reciprocal of that denominator, which is going to be x minus 1 squared all over negative 1. Okay, okay. So then I'm looking at e to the limit as x goes to 1 from the right of negative, I guess, x minus 1 squared all over x ln x. And what is that form? So in the numerator, it's 0. And in the denominator, it's, if you plug in 1, you'll get 1 times ln of 1, which is also 0. Right? So that's a 0 over 0 form. You can do L'Hopital's. So we'll have e to the limit as x goes to 1 from the right of, in the numerator, you have negative 2, it seems like I made a mistake somewhere, but no, I'm good. Negative 2 times x minus 1, and the denominator you got to do a product rule. So that would be ln of x plus, so what's the derivative of ln of x? It's 1 over x, but then times the other one, which is x, which is just 1, right? So then you check it again. So in the numerator it'll be 0, and the denominator will be 1, so that's just 0 over 1, which is 0. So you end up with your answer as 1. Seems like 90% of the time your answer is either 1, or it's E, or it's 0. But it takes a lot of work to get there, right? So that was the quiz question for 5.6. We're not going to do 8.7, if you're wondering what happened. We're skipping 8.7. That's basically just, can you read a table? And because we have computers now, it's unnecessary for us to do that. So we're going to skip 8.7. We're in 5.6 right now. Okay. Okay, last form then are these infinity minus infinity forms. Like, we can figure out infinity plus infinity, but infinity minus infinity is a bit different. So infinity minus infinity, or negative infinity plus infinity, those forms where one is fighting the other. So let's take a quick look-see at this type. And usually the trick is to just combine the two terms into one term. So maybe I should write that. Combine two terms into one. You have all kinds of ways to do that. Find a common denominator. You can, what else? Use natural log rules. So ln of a plus ln of b equals ln of a times b. You know, so you got a couple tricks up your sleeves. Once you do that, you can just use L'Hopital's. Okay, so let's look at one. Right. Example, we have the limit as x is going to 1 from the right of 3 all over ln of x minus 2 all over x minus 1. Okay, so first I'm going to figure out the form. Ln of x, you know, as x goes to 1 from the right, where does ln of x go? So there's 1, 0, right? That's 1, 0. So as x goes to 1 from the right, ln of x is getting closer and closer to 0. So you'll have like 3 all over 0.1, 3 all over 0.001, 3 all over 0.0001. In other words, infinity. It's L over 0, so it's going, in this case, positive infinity, minus wherever the heck that other guy's going. So we have the limit of 2 all over x minus 1 as x goes to 1 from the right. Okay. So this, again, is L over 0. I just have to do like a test value thing here. So 1 coming in from the right, and maybe do a little table to help me out. So something like 1.1, that'll be positive 2 all over 1.1 minus 1 is positive. Positive over positive is positive infinity. So I have infinity minus infinity form. So yeah, it's one of these forms, so I can do, I have to do something, and I'll find a common denominator, right? So limit is x goes to 1. This guy needs an x minus 1. And the other guy needs an ln x. Okay. So we'll have what? 3x minus 3 minus 2 ln x all over x minus 1 ln x. And then investigate the form, right? So in the numerator, I'll have 3 minus 3, 3 minus 3 minus 2 times ln of 1 is 0. So that'll end up being 0. Right? And then in the denominator, I'll have 1 minus 1 times ln of 1, which of course is 0. So it's 0 over 0 form. What does that mean? That means do L'Hopital's. Okay, so limit as x goes to 1 from the right of 3 minus 2 over x all over derivative of, I'm going to distribute first. Okay, so I have x ln x minus ln x. The derivative of that, the first part, you need a product rule. So that's x times, well, let's take the derivative of x first. So it's 1 times ln x plus, leave x alone, times the derivative of ln of x. And then minus the derivative of ln of x. Okay. So what does that equal? That's ln x plus 1 minus 1 over x. Okay. So I have ln of x plus 1 minus 1 over x. Okay. So in the numerator, I'll have 3 minus 2, and the denominator will have 0 plus 1 minus, that's 0. It's L over 0 form. I just got to figure out if it's going to positive infinity or negative infinity. Okay. And it looks like it's going to be going to positive infinity, because this number will always be positive, the ln of x. I mean, if you get really worried about it, you can just literally find common denominators and get rid of the fractions. Right, so maybe we should do that. Let's do that. So I have 3x minus 2 all over x all over x ln x. Is that going to just get me back to where I was? X minus 1 all over x. So that will equal the limit as x goes to 1 from the right of 3x minus 2 all over x ln x plus x minus 1. I just multiply top and bottom by x after that. So the numerator is 1. The denominator, this part will always be positive for your test values. So you're testing like x equals 1.1. That part's positive. This will be 1.1, and then if you subtract away minus 1, it will be 0.1. So it'll be a positive plus a positive, which is going to be a plus. Okay, so in other words, it's going to go to positive infinity. If you just look at some test values, put it in your calculator, 1.1, 1.01, and you'll end up with infinity. Okay, so that does it. My voice is going. I'm going to call it quits for this video. And thank you for watching, and hopefully I'll see you next time.